Any questions on homework, anyone? Anything lingering? All done? All done?
How detailed does the report have to be?
Like sufficient for us to understand your strategy, okay, and that be convinced that you actually did it and not simply report the answer from someone else. So kind of just, yeah, but I would imagine probably like a page or two, something like that. Yeah. Yeah, I am still kind of trying to figure out because when uploading .zip to Greatscope, it attempts to run the container behind, so I'm trying to set things up, so it should be there. Yeah. Worst come to worst, I'll have a Dropbox link to post. So, okay. I think there was a question about can I use Go language? Yeah, when you can use any language. So anything that we can run. Okay. Let's proceed with the first one.
All right, hello everyone. My name is Kean Costello. Today I'll be talking about packet level signatures for smart home devices. This is a paper that came out of work done at UC Irvine by the following contributors, and they present the ping pong system, which allows you to uniquely identify packet level signatures for any of these smart home devices. So a little bit of background and introduction. Smart homes are becoming increasingly popular. Many of you will probably have smart devices in your own house, and they connect to internet via Wi-Fi, and they're often controlled by smartphones or voice assistants. For these devices, the network traffic is encrypted, but they're still susceptible to passive inference attacks, and user behavior can actually be inferred from network traffic. Currently, there's a few limitations to this kind of passive inference attacks. One of them is it's difficult to identify the exact type of event or command. Oftentimes, it's only valid for certain devices or manufacturers. And a lot of attackers will require more information, either the protocol or the source code for these smart devices. And there's different mitigation strategies such as traffic shaping, which can prevent traffic volume analysis. So first of all, a little bit of related work before I talk about the ping pong system itself. HomeSnitch was a paper that identified IoT activity through statistics from the entire client-server dialogue. Something important to note about this is that the most important feature that they determined was the average number of bytes sent from the IoT device to the server. And as we'll see, ping pong also uses the length of the number of bytes in a packet as the most important feature. There's other papers that are specifically for a single device, so the Nest Thermostat, Nest Protect, or for Zigbee and Z-Wave. And a lot of the other papers use machine learning and statistical analysis techniques which cannot differentiate between different event types. So here's the problem setup. The communication can occur in three ways. There's between the phone and the device in the cloud, and the phone in the cloud. And in this case, there can be two sniffers, one in the local network, the Wi-Fi sniffer, and one in the wide area network, or the WAN sniffer. So in this case, the Wi-Fi device is going to be on the right, and they can sniff at any of those two locations. And they're going to actually initialize and initiate events from the smartphone itself. So they're going to assume that the adversary knows the type of smart home device that they wish to target, which is very important because in order for ping pong to work, you have to train on the actual type of device you want to use, and you'll be doing this training offline. And we're going to assume that the devices will encrypt the communication, but a lot of things like the MAC address and other things like that won't actually be encrypted, so you can use that information to your advantage. So what they noticed is that oftentimes packet level signatures come in pairs. There's going to be a packet in one direction, which is a request, and there'll be a reply packet in the other direction. This is where the name ping pong comes from, like a back and forth kind of exchange in a ping pong game. So as you can see here, there's a packet exchange for the toggle on and toggle off, and the difference is the number of bytes in that packet. So 1,117 is sent, and then 613 is received, versus 1,118 is sent, 613 is received. So this is just one example of a pretty simple send and receive packet pair. You can see they uniquely identify an event. So here they were able to determine that one was toggle on, the other was toggle off. Yeah.
But thus far, it's not any different than one of the techniques in the related work again, right? The number of bytes being sent.
Yeah, well, that one incorporated the entirety of the network traffic. This one is going to actually filter and cluster and isolate them. So it is, I'll get to how it's different, yeah. All right, so the first step in the training is to get the entire network trace and then a text file of event timestamps. So we're going to collect this trace, and it will include both local traffic and internet traffic, and then we need to filter it. So we're going to actually discard traffic that's unrelated to a user's operation of a smart home device. So we can drop packets where the source or destination IP address does not match the device or controlling smartphone. And we can drop packets that do not lie within 15 seconds of the event timestamps. So this 15-second window, they did a couple of calculations. They figured that even with network delays, an event wouldn't take more than 15 seconds to actually initiate the request and the reply. And so basically, you're able to filter out all the background traffic, all the background noise that's not related to an actual event, such as an on or off of a light bulb, let's say. So from these packet pairs, we were able to capture the request-reply exchanges. And then they used a clustering algorithm, DBSCAN, which stands for Density-Based Spatial Clustering of Applications with Noise, to actually compare the similarity of two packet pairs. So the maximum distance between two packets will occur if the directions are different. We don't want to match any packets that are, one is a request, the other one is a reply. And then if the packet directions match, we're going to use this Euclidean distance measure to get the distance between pairs. So here, the P refers to the actual packet length, and P of ij would refer to the ith element of the pair j. So in this case, you can see the first element of the pair 1 is compared to the first element of pair 2. In this case, it would be a request. And also the distance of the second element of the pair 1 and the second element of the pair 2, which would be the reply. They determined that for the DBSCAN algorithm, there's two main parameters. One is the radius, the other one is the min number of points. They determined through experimentation that the radius of 10 works best. And also, for the minimum number of points, they determined it was n minus 0.1 n. So if you have 50 points, 50 on and off actions, you would have between 45 and 55 as the minimum number of points. So here's a pictorial example of how the clustering works. So as you can see here, the DBSCAN algorithm identified two clusters and some outliers. The most important part about the clustering is that just because we have a cluster doesn't mean we're going to actually go ahead and create a signature from that. As you can see here, the frequency here was 98, and the frequency there is 50, so we only have 50 events, so we're going to disregard the 98 in this case, because this is going to be considered chatty communication. So these frequencies that are outside the 45 to 55 window are going to be chatty devices, and they're not going to actually correspond to events that are within the time window and events that should be labeled as a signature. So this example, we don't actually concatenate any packet pairs. As you'll see on the next slide, they normally are concatenated to get the longest packet sequence, and we'll do so if it occurs consecutively within the same TCP connection. So thus, you can see we'll form a temporally ordered list of packet sequences here. So you can see there's packet pairs, pair 1.1, 2.1, that form one sequence, and then there's also a packet pair 3.1 that forms another sequence, and this occurs after the first sequence. So this thing as a whole will be the packet signature for this event. So in order to validate this algorithm, we're going to use a detection algorithm. And you're going to basically detect at most n events with matching timestamps. And this will lead to a valid packet level signature. This signature can fail if there are false positives. And the way the detection algorithm works is there's a state machine for each packet. And if the packet's length and direction match that of the packet in the next state, the state machine will advance and record the packet. Once the state machine reaches the terminal state, the set of recorded packets is considered a sequence match. It's interesting, the paper decides to treat layer 2, which is the Wi-Fi, and layer 3, which is the wide area network, with different protocols. So in the case of the Wi-Fi sniffer, it'll ignore a wrong packet, so out of order packets can actually cause failures. Whereas for the layer 3, the wide area network, the state machine will discard partial matches. And in order for the detection algorithm to be more efficient, they'll bound the number of state machines possible and minimize false positives by basically taking an existing state machine state, and if there's one with a later timestamp, they'll use that one instead. There's two types of packet matching techniques. One is exact, so we're going to have exactly 339 bytes, and there's another one that is range-based, so we can have a small range that allows for differences in user credentials or device IDs. The sequence matches must obviously occur in the correct order, and simultaneous events do not actually cause problems for ping pong. This is because in the filtering stage, incoming packets are separated into different sets by device. So they're going to look at the TCP connections to the MAC addresses to prevent simultaneous events from causing problems. Okay, so for the evaluation of this system, they used data from 19 different devices, 11 which are the most popular on Amazon. And they were able to get unique signatures for 18 of the devices through their automated process. So filtering, clustering, validation. And the only device that they failed to get a signature for was the LIFX light bulb. And this was because it uses UDP, which is connectionless. There's not going to be a typical request reply. There's no acknowledgement pattern that you would normally see in a TCP connection. So here's an example, this Amazon plug turning on and off. There's 2 sequences. Off, there's 3 sequences. It's device cloud interaction, and those are the minimum, average, and maximum time of transmission in milliseconds. So as you can see, it takes between 1 to 4 seconds for this request reply sequence to occur. In order to test the data, they use a testing data set of 13 devices, and they use an additional 12 for background network traffic and 6 more for background event triggering. So basically trying to generate as much noise as possible to filter out exactly what you want. And they triggered 100 of each type of event for the testing, and they were able to get a false positive rate of 0.18 for the wide area network and 0.32 for the Wi-Fi sniffer. Another thing they wanted to do to make sure the evaluation technique was correct is they used a negative control. So they used 3 open source publicly available data sets, UNSW, YourThings, and UNB, to evaluate the uniqueness of signatures. And as you can see here, they found very few false positives based on the number of packets, maybe 0 or 1 false positives, and there's the order of 10 to 100 million packets. This is for the wide area network sniffer. The Wi-Fi sniffer, there were about 11 false positives in 400 million packets. And as I mentioned before, this is because the layer 2 policy is more relaxed and actually ignores the unmatched packets instead of just dropping the entire partial packet. They also explored home automation, which is the if this, then that. So basically automating your smart home. If you walk in the room, you want the light to turn on, etc. And out of 13 supported devices, they were able to get signatures for 9 devices and 12 event types. They determined that signatures are pretty similar for similar devices, but they're still distinct across different models and event types, so it's not going to disrupt the ping pong system. They also evaluated on the state-of-the-art IoT-R monitor dataset, which is a state-of-the-art public dataset with 55 devices. The first thing they did was filter this dataset. They removed devices with empty or limited network traces, and they removed devices that communicate via UDP because, as seen before, this pretty much only works for TCP connections. Of the 26 remaining devices, they were able to extract signatures for 21 of them. And one of the things they noticed was they actually encountered sequence of packet pairs with the exact same pair of packet lengths for the same event. So that's going to actually mess up the clustering algorithm, and in order to fix that, they have to account for the timing of packet pairs in the same cluster. They were able to use relaxed matching for packet lengths that differ with user credentials. So if my smart home uses my username as part of the packet header, and then Runal's uses his username, they're going to be different. So we can add a variability measure there to get us to actually match the same signature. And they also found that some signatures change over time as firmware updates happen. So this is one of the limitations of ping pong. And in this section, they also described how they validated the dbScan parameters of the radius of 10 and 0.1 n as the variability, as well as the time window of 15 seconds. So there's a few defenses that can be used against the ping pong system. 2 of them I'm going to mention first: traffic injection, where you add dummy packets to look that looks similar to real events, and then traffic shaping, where you delay packets to confuse temporal inference techniques. The most obvious defense for ping pong is packet padding, because ping pong relies on the actual packet lengths to determine unique signatures. So in packet padding, you'll add a fixed length, a random number of dummy bytes to each packet. And they use a VPN-based implementation, so basically as traffic leaves the device or enters the network, you're going to pad the packets at that point. They used one example, the TP-Link plug, and they were able to actually generate 1,900 false positives for each event. Now granted, they used a simplified version of ping pong that didn't consider packet lengths, but as you can tell by this one example, the approach works pretty well for devices with short signatures. And finally, they present some future directions. First of all, they can find similar known devices instead of acquiring the new device in order to apply ping pong to extract the signature. Right now, if you want to use this in an adversarial attack, you'd have to buy the smart device yourself, go ahead and train it and test it on your own, and then you can try to acquire data from someone's smart home. So they want you to be able to use a similar device or one that's already in their database and go from there. They can relax matching to account for signatures that evolve over time. They have experimented with training different configuration patterns to apply relaxed matching, again, to account for credential or device ID variability. And the last thing they can do to make the algorithm more accurate is to profile or subtract background traffic during signature creation itself. That's it. Any questions?
So I don't understand quite the UDP part, because since UDP is there is no ACK, so the application would still be doing an ACK, right? Otherwise, the whole system becomes unreliable. So don't UDP devices still have ACKs, just that it's at a different layer? Yeah.
So they're focusing exclusively on this exact request reply pattern. So it has to be one after the other.
Okay.
So their ping pong algorithm can't pick up an ACK that comes later. They're looking for that exact request reply. So I think one of the extensions could be to implement it for UDP as well. But as of right now, they're focusing on TCP because, as you can see...
I guess what I'm saying is, I would imagine most UDP devices would have an app-level ACK which comes immediately, because otherwise there is no reliability in that exchange, right? I mean, it's just that instead of the TCP layer doing the ACK, I would imagine with the app layer. But anyway, okay. No questions? We move on to the next one. Thank you.
Yeah. Okay.
Okay, hello, I'm Ria, and today I'll be giving a presentation on Flowprint, which is a semi-supervised mobile app fingerprinting technique on encrypting network traffic. So a fingerprint is basically like a screenshot of an app activity which shows, which tells us information about the operating system and the user agent, and sometimes even the screen size. So Flowprint is a technique to construct those fingerprints of the apps for an encrypted network traffic. And this technique is novel in the sense that it is even including browsers, something that had not been researched a lot in the previous works, and it can even detect unseen apps. So it uses a temporal correlations among the destination related features, because it feels that destination related features are very unique and they can generate fingerprints and help in its detection. So it shows an accuracy of around 93.5% for unseen apps, where 72.3% of them are detected in the first 5 minutes. And for the apps that have been seen before, it shows an accuracy of 89.2%, which is better than the existing solutions that have been that were discovered before this. So it generates fingerprints from mobile network traffic. Now, there are some problems with mobile network traffic that complicate the process of generating fingerprints. Firstly, you need prior knowledge. Encryption complicates things a little bit. Various apps have some common modules. That also complicates the process a little bit. And then there are various versions of the app. They're installed and uninstalled. So these make the process a little bit complicated. And you can see there are some parameters like homogeneity, it being dynamic and evolving. Homogeneous means that there are some common modules which are shared, and that is why it becomes difficult to detect one from the other. And that's also because most of the apps are using HTTP. That's why they are using destination related features, because that is unique for various apps. Second thing is dynamic. Dynamic means that it is influenced by user activity. That influences the network traffic. So again, destination related feature is one thing that the users have very little control upon. So they can use that for the fingerprint generation. And thirdly, apps are always evolving. Evolving here means there are different versions which are coming out. So what they do is that they are creating patterns out of the network traffic, which depends on the app. That is why even the fingerprints evolve with the changing versions, and it makes it more accurate. So they use they use variety of data sets because they wanted to generate fingerprints for various across various areas. They used Recon, which has various Android applications and even has its different versions. So they used it to see the performance on different versions, and they collected the data for over 2 weeks. Then they used cross-platform data set, which contain apps from both Android as well as iOS, and each app was executed for 3 to 10 minutes to generate traces and inputs. Third is Androbis. Androbis has apps which are both benign as well as malicious. So they wanted to see how well it performs in case of malicious and benign apps. And they use Android Exerciser Monkey to generate the user inputs, and they ran each app for 4 minutes. And finally, the new thing that they have introduced is browser. So they took around 1,000 websites from Alexa which were streamed over Google Chrome, Firefox, and Safari, which account for about 90% of the browser traffic. Next technique that they applied is feature exploration and
in browser, are they trying to fingerprint the browser or fingerprint the websites within the browser?
They are fingerprinting the browser, sir, because what they are saying is that it generates a lot of web content, and the browser activity can be taken as considered as one app. So this is feature exploration. One thing that I forgot to mention is that they are using that the network traffic has TLS, so they are using this transport layer security. That's an encryption technique, but using that means only the size and temporal features can be leveraged, and they even had values like minimum, maximum, mean, standard deviation, and absolute mean, and percentiles, of course. Next is feature ranking. Because they are detecting unseen apps and there is an element of unsupervised learning, they use adjusted manual information for scoring the features, and that's preferred over information gain, because information gain gives some preference to randomness, which is not preferred in this case. And AMI defines the relative amount of entropy when you know a feature with respect to a class. So the class over here is app. So this is the equation. But because they want to remove the bias also, that is why they normalize it by adding entropy, that is h of x, as well as expectation value. Next is feature evaluation. So these are the features which have been used. Because the destination related features can be unique, they even leverage the temporal things, temporal characteristics. And if you look at the table, none of the AMI values are even near 1. So that is why they have to use a combination of values in order to extract for feature extraction. So interflow timing and packet interarrival time are some of the important features which are used. Next is device. They are utilizing the device feature in order to reduce the dynamic nature of the traffic. They feel this is more accurate, and IP address can also change, so that is why they are doing it on a per device basis. Third is destination, where each app interacts with various servers and it has different modules corresponding to destinations. So that can help in creating the fingerprint. And for size, the incoming and outgoing packet size are important, but the other packet sizes do not contribute much. That is why size is not used as a very big factor for fingerprint generation. The thread model that they constructed is as follows. they feel that they can trace the backflow to the device despite the changing IP address. They can detect the mobile from the non-mobile devices, and they'll essentially be working on the same network. And this research is based on only one app being active at a particular time. For multiple applications, there is still research going on, and it's even a ground for their future work. So the first step is feature extraction, where you utilize where you analyze the TCP UDP traffic, and you're extracting features like the TLS certificate, IP address, as well as the port number. And timestamp is used for temporal correlation, whereas these features are used for clustering. So clustering is a phase in which the input data is divided into T batch. Sorry, that's a typo. And then they extract the features of each batch. So the clusters are correlated if they have the same. The flows are clustered together if they have the same tuple, where the tuple consists of the IP address as well as the port number. And sometimes there are even cases of shared clusters because of multiple app generation. A third is browser isolation, and for browser isolation, what happens in browser isolation is often it generates more content than the user had asked for. You have advertisements, and then there is uploading and all that. So they are isolating the browsers and analyzing them separately, and they use features like relative change in the active clusters, relative change in the bytes uploaded, relative change in the bytes downloaded, and the ratio between the upload and the download. Fourth is cluster correlation. So here they use both destination as well as temporal features, where they say that at a particular time it will have a unique destination, and that unique destination, and then they will cluster them based on this equation. So this is the equation for clustering them together. They are basically clustered if they have the same IP address and TLS certificates. You can see the graph. So here a node represents a destination related cluster, and the edges that you can see is based on the correlation between two clusters. So some of them are weak, and some of them show some of them are darker, showing greater amount of activity. Then for generating the fingerprint, they remove all the edges which have a weak correlation, and there is a parameter that is a T correlation. It is about 0.1. So if it is lesser than that, it is classified as weak and it is removed. Then cliques are referred to the strong edges or the strongly correlated clusters, and then you extract the IP address, port, and TLS certificate. Finally, you have fingerprint correlation. That uses Jacquard similarity. So FA and FB are two fingerprints, and this similarity is given by the ratio of the intersection to the union to show similarity. And if it's above this threshold, this means these fingerprints are same and they belong to the same applications. Next step is evaluation. So first, these parameters are used. T window refers to the time for which a browser is considered active or not. And for a browser to be considered active, it has to send or receive messages from the browser for a particular time. So in these cases, one of the hyperparameters was set as constant. Except for one of them, the other parameters were set constant, and then the model was trained to find the optimal value of the parameter. Once that was set, the others were trained as well in similar fashion. For app recognition, they will create the fingerprints, and then they will even test it on the data set. And for detecting the similarity, they use Jacquard similarity, and they use random forest classifier for this. For unseen applications, what they did is they just saw whether the applications have been seen before or not, and when they are not, and if they don't relate to the data set, this is given by threshold T new, which and if it's below that, then it means it hasn't been seen before, and then its features are extracted, fingerprint is constructed, and it is added to the data set. And this is the graph where the number of fingerprints show whether belongs to an app or not. That is called cardinality, and the analysis of effect of cardinality is another ground for future work. And confidence level shows how how confidently we can ascertain whether it belongs to an app or not. So H gives the entropy of an app when the fingerprint is known, and when confidence level is 1, that means we can ascertain that it belongs to that particular app. Next is mobile network traffic challenges. For homogeneity, a lot of clusters showed shared activity, which is why they were clustered together, and they were just 39% of the clusters. But together they were about 56.9% of the flows in the data set. But even if you remove the non-shared clusters, the accuracy and F1 score were not dropping because the correlation patterns are unique. So this means it can counter the problem of homogeneity. For dynamic, the user-generated traffic creates unique fingerprints, and they were able to show that between the automated and the user-generated data sets that they use, there isn't significant drop in the performance. And again, the destination features are something that the users have no control on. Same for the advertisements and all which are present while launching an app. Finally, for evolving, they got traffic every 2.5 months, and they found out that with an app update, if they also change their data set, and then immediately, then it can recognize 95.6% of the fingerprints, and even if they don't, 90.2% of the fingerprints are still recognized, and this is over a period of 1 year. That means they have sufficient time to update their update their research and make it better. Then they wanted to see the effect of the training data points on the performance. And what happens is, as you increase the number of apps, there is an increased possibility of shared activity. That is why you can see that the precision and accuracy is falling down. In case of unseen apps, initially the recall is affected because of the new data that is coming from the unseen apps, and initially it falls because when you add more data, there is a greater possibility of the app belonging to the data set. But once the training data set has enough data points, you will see that the performance becomes stabilized. Finally, for execution time, even though clustering and cross correlation have a complexity of O(n) square, you can see that the graph is linear. That is because for clustering we are utilizing the destination related features, and they implement a hash map which is implemented linearly and has a time complexity of O(n). And for cross correlation, if they have the same activity, their mutual cross correlation is 1. And again, even this was shown linearly. That is why you can see that despite the complexity of O(n) square, you can see that the graph is linear. So some of the strong points of this research is that it was conducted across various various fields like Android and iOS applications, various updates of the same app, malicious and benign apps. It is also able to include browsers in it and detect them. It is able to detect unseen applications as well, and it is even robust against destination network inconsistencies. And some of the limitations are that it only works for a single app activity at a time. So for multiple app activity, there is still some research work that could be done in the future. And other than that, one of the parameters that I spoke about, the T batch, for which each batch is trained before the clustering, the optimal value was set to around 300 seconds, which is around 5 minutes. So if you reduce the time, that shows a trade-off in the performance. That's one of the limitations. In case of malicious apps, they can detect it, but if a malicious app is packaged under a benign app, then there will be some problem in detecting it, and there's some future work going on in that as well. And this is one of the things that they could also focus on in their future work. And finally, the number of fingerprints that are used to ascertain whether it belongs to a particular app or not, that optimal number or range hasn't been specified. And they can work on this to determine that optimal range, and even the current research work is also going on in that. Thank you. That's all from me.
Questions, anyone? Everyone quiet. Okay. So, and are they able to handle things where there are multiple devices on the network at any given time, or like, is it only just an issue like you need traffic from a single device, or you can give you traffic which is intermixed with a whole bunch of different devices on that network?
So they haven't talked about multiple devices on the network. In fact, they're even saying that when there are multiple apps which are active at a certain point of time, it will be difficult for them to create the fingerprint and classify them.
And
Because
why is that? I mean, I didn't fully understand that part. So why can they not separate based on port numbers and things like that? What all is visible to them from the packet?
so they can see, they can
They
extract
can see the IP address,
IP
but they
address.
also can see the port.
The port addresses
Right.
as well.
So different apps have different ports, and therefore separated out.
Yeah, so that is possible, but another thing that can happen is that they can have some common modules that are there. So the common modules, because a lot of them are implemented by CDNs, content delivery networks, and third-party services, and that generates a lot of network traffic. So even the increased network traffic complicates the process of fingerprint generation and classification.
Great. Nothing else? Then thank you. Okay, let's move on to the next one.
Hi everyone. Sorry, I'm a bit nervous.
Just relax.
Okay, sure.
Relax. Take your time.
I would like to present a paper called Dataset, Establishing Physical Function Virtualization to Disrupt Reconnaissance of Power Grid's Cyber-Physical Infrastructure. So what this paper proposes is a sort of defense mechanism to make it very difficult for an attacker to learn the underlying structure of a smart grid network. And I would like to divide my presentation into these parts, and let's first start with a brief introduction of the context of this research. So as we have seen in class, there has been a lot of smart power grid stuff going on around us. Like we have smart meters, and also we have smart devices controlling the power stations. And those devices, since they are so crucial in our daily life, they become a target for attackers. And for an attacker to mount an attack, he first needs to learn about what this underlying structure is like. So he has to do some kind of reconnaissance effort. And there are actually already some approaches that offer defenses against these attacker reconnaissance, but they either lack the interaction with the environment, or they are completely static, meaning just like a honeypot system sitting there, or they may fail to model system level behaviors, for example, the latency in the system. And what Dataset proposes is this thing called physical function virtualization. What this does is that it will add some virtual node in the network that will simulate the behavior of real devices. They do this to increase the reconnaissance difficulty on the attacker's part. And those virtual nodes are backed by real devices to make it look more realistic. Now let's move on to the threat model of this scenario. So the assumption here is that the attacker will gain access to one of the elements in this smart power grid system. For example, maybe it's called remote something unit, well, anyway, it's just the attacker will gain some access to part of the system, but
RTU stands for remote terminal units.
remote terminal, yeah. Yeah, exactly. Yeah. Thank you, Professor. But just from these devices, he's not able to tell the entire structure of the network, and so he has to mount some kind of reconnaissance beforehand. And there are mainly three types of attack covered in this paper. The first one is called passive attacks. Basically, it's just packet sniffing, like monitoring the current network traffic. And the second type of attack is called proactive attack. Well, it's just probing the network to see what is present and what is not in the network. And the third type is called active attack. What the attacker will try to do in this type of attack is they will either try to attack existing network packets, or they will try to inject some false packets into the system to make the controller think that there's something going on in the system. And now let's move on to the design of DevRec. So to address the first type of passive attack, DevRec will the main goal of DevRec is to significantly increase the reconnaissance effort. And for the second type of probing proactive attack, the goal is to be able to detect and isolate the attacker. And even if these all fails, and the attacker is actually mounting an attack, DevRec will be able to craft some decoy data to render the attack ineffective. And now let's move on to the components of the system. So as we've mentioned earlier, DevRec inserts some sort of virtual nodes into the system. And to insert these virtual nodes, you first need a template, which includes the network stack information, for example, the IP address, and also the application layer protocols. It just means how this node should interact with other nodes within the same network. And also, to make this look more realistic, you will need a profile of the seed device. For example, what kind of protocol has it implemented, and also some system invariants, such as the latency. And on top of that, you also need some physical state variations. For example, the voltage fluctuation, because if you have a virtual node that's sending out a constant voltage, the attacker will be able to tell that it's a fake node. Like it's just sending out a fixed voltage. So we need these sort of variations as well. And for this to work, we'll need a thing called packet hooking. It's based on the software design networking programmability. So first, we'll need a protocol parser which reads the packet headers, and once we have that information, we'll need a traffic regulator to redirect the packets that's sent to those virtual nodes to the underlying real devices that's backing these virtual nodes. And after that, we'll need some protocol encoder to simulate the behavior of a real node in the network. So we have these three that's helping us implement the entire solution. And now let's move on to how the researchers actually implemented all these defense mechanisms. So to address the first type of passive attacks, which is just eavesdropping on the network traffic, they have something called randomized request pattern. What they do is just they will issue requests to randomly selected, like both randomly selected real device and also virtual nodes. Doing this is to sort of balance out the number of requests sending to both the virtual and the real devices. For example, if the attacker sees that there's tons of traffic going to a fake node, he will know that this node is fake because there's just so much traffic going into it. And And the requests that we are sending, they're just very harmless requests, like just maybe getting some basic or necessary measurement, and also the researchers are able to show that the impact of sending these requests on the system is minimal. Like they are still able to achieve a 99.8% accuracy on normal control operations. And to address the second type of proactive probing attack, they have something called a probabilistic dropping protocol. So what this does is that when an attacker is trying to probe the network, he will inevitably run into some inaccessible nodes. And once he does, DevRec will label this entity as suspicious, and will drop its packet with probability P0. And if this type of illegal access continues for the kth time, they will drop the packet with the probability of PK. And also we have a threshold, like that will be the maximum allowed illegal access. And once we go above this threshold, you will know for sure that this must be an attacker, because under normal operation, no one would try to access these inaccessible nodes that many times. And now it's the most, I would say, math-intensive part. It's to defend against those active attacks. So to counter those type of attacks, we first introduced a linear measurement model. Like in that equation, you have x, h, and z. X is the underlying system state, and h is a measurement matrix, and z is a corresponding measurement. And what the attacker will try to do in this case is that they will try to inject some packets containing these measurements, and they will try to send this packet to the controller to make the controller update the system to a false state, so to achieve their attack goal. And actually, modern systems are already implementing a sort of defense against these bad measurements. Is that in this measurement model, we allow a sort of error term, and when this error term exceeds a certain threshold, we'll say that this here is a bad system measurement, and we'll simply ignore this measurement. And what the attacker will try to do is that they will try to design a certain measurement that will keep this error term below the error threshold, so that controllers still thinks that this is a valid measurement, but in reality, it's some false information. And what we can do to prevent this is that, as you can see here, we have the actual devices measurement and the actual devices state, and also we have our decoy devices measurement, decoy devices state, and decoy devices measurement. So once the system receives a certain measurement, he will try to compare this, like, to get this term, you will need these things tied together. And when you see that this term is changing because of your decoys changing, you will know that this for sure is an attacker trying to mount an attack on the system. And it's not the measurement actually reflecting the change in the underlying system state. So this is how we can defend against active attacks. And now let's move on to the results of their experiment. So as you can see here, they have actually implemented this on some real physical systems. Like you can see here, they have certain switches, and they have those software-defined networking software, and also actual devices which you'll see in a real smart power grid, like relays, PLCs, meters, and they have actually implemented a valid network topology right there. And the result, first, is how closely these virtual nodes resemble real devices. And as you can see on the probability distribution right there, the sort of orangish color is our virtual node, and the bluish color is the real devices. as you can see here, our virtual node actually matches the real devices very closely. So the attacker will not be able to tell that this here is a fake node or a real device. And the mean also matches quite well. And here is the I would say here's the part that differentiates this from, say, a honeypot system, is that we actually have voltage fluctuations in our measurement. So that will further confuse the attacker into believing that this is real measurement on real devices. And also, now let's move on to the effectiveness of the attack. As you can see on the graph here, even if we inject just 10% of virtual nodes into the system, we can already delay the attacker's attack by 100 years. And if we continue to add more virtual nodes, the delay will easily go beyond 1,000 years, which is almost impossible to crack, as you can see over there too. And here is the performance against active attacks, and here is how much of the measurement should the attacker tamper with to get the false negative rate below 0.5% or above 0.5%. I can't really remember, but this is just showing that DevRack is able to defend against both passive, proactive, and active attacks. And now let's move on to the performance overhead. As you can see on the throughput, round trip time, and also latency here, implementing this DevRack doesn't introduce a lot of overhead on the system. So yeah, so it's actually a quite good defense mechanism. And now, finally, let's move on to the limitations and future works. As the author has said in the paper, their virtual nodes is only modeled after certain vendors' devices, and in the future, it can be expanded to like more vendors to make these virtual nodes more realistic. And the power side channel attack we talked about in class is actually not addressed here, because even though you have virtual nodes, the smart meter can still leak your privacy information, which can be researched in the future. And lastly, this type of virtual node defense can be extended to more industrial control systems. Like right now, it's just smart power grid, but in the future, probably something else, like in the factory and other stuff. And that's all I have. Any questions?
Thanks.
Yeah.
Questions?
Yeah, please.
Yeah. That was a good presentation, by the way.
Okay, thank you.
I was curious about where they were getting this metric for hundreds of years, thousands of years.
I'm actually curious about that too. But in the paper, they didn't say how they got this type of information. I'm guessing this is kind of same as saying to crack a certain encryption protocol, you'll need certain years or something. So I would say this is kind of similar to that. Just
Yeah, they probably have some Azure model and then.
Yeah.
And then that,
yeah, please.
So in one of your implementation slides,
Yeah.
please clarify the 99.8% accuracy.
Oh, that is just since we are introducing these additional random requests. One concern is that these additional random requests could affect the performance of the actual system. And what they're saying here is that even with these randomly added devices, if you want to control the system, you can still control that 99.8% of the time. Yeah. Yeah, please.
This is more of a, I don't, like, not to you, but just like general question.
Okay.
Is 99.8 good enough? Like, do you know?
on a system like this, yeah, that's an interesting. So these are safety critical systems, and
Right.
99.8 is not enough.
Yeah.
Right. I mean, because I think these things typically aim for 4 nines or 5 nines
Right.
reliability. Yeah, so you're right on. So yeah, good point. But at least I guess they're considering it. And maybe the other way of looking at it is the following, that in the presence of adversarial attack, what the reliability of these systems is probably worse. So when we normally say that they have 4 nines or 5 nines, it's not under adversarial situations. So I think depends upon the yeah.
Does it make sense to like enable such a thing when like you detect like an attack is being tried to?
Well, so in a way they are detecting the attacks, right? So the question, maybe another way of saying what you're asking is there a lighter weight scheme which can say, okay, possibly an attack is happening and then let's switch to this. The challenge is that, if that scheme has a very high false negative, then you're worse off. These kind of issues, exist in essentially, in this case the context is obviously power grid and all, but probing enterprise networks and all, these are all so this notion that you have to protect the details of your internal structure is relevant in many other contexts also. So and yet you want to do it without disturbing your code. The other issues in these settings you might also imagine is the following, that I guess there is an underlying assumption out here that the adversary is remote, and so whatever actions it is doing and all, it can't see its effect. But what if I was trying to hack into, let's say, LADWP, and I do something and I don't see the impact of it, then I would immediately know that perhaps there is some defense mechanisms like this, and then I can say maybe that node I'm attacking is actually a virtual node because I'm not seeing any physical effect. So, so these kind of systems are kind of assuming that the adversary does not have an independent pathway to look into the physical things. But still better than nothing. Is more sophisticated. Okay, good. Thank you.
Thank you.
Okay. That was
Hi, my name is Mrinal, and I'll be presenting Deep Bin Diff. It's a learning program-wide code representation for binary diffing. Hopefully, like, you guys had some encounter with binary diffing in the homework and things like that. So, yeah. So, what is binary diffing? Like, the definition is like given to input binaries, precisely characterizing the program-wide differences by generating the optimal matching among basic blocks with quantitative similarity scores. Like, that's a mouthful. So simply put, it's just finding the similarities and differences between two binaries. And it works at a basic block level. A basic block is basically a series is a series of instructions that have a single entry point and a single exit point. It's super useful when you're doing like code transformations and other compiler optimization. So compilers basically essentially generate a bunch of basic blocks and then work with those. Where am I? Oh yeah, there's tons of applications for binary diffing in like security scenarios. Where program-wide analysis is required, such as locating the change parts of a binary, or malware analysis, or security patch analysis, or binary-wide plagiarism detection, or just patch-based exploit generation. Binary diffing does not only provide like precise, fine-grained quantitative results, but it also explicitly reveals how the code like changes across different versions, or different levels of compiler optimizations and things like that. So yeah. So what is the current status of the world of binary diffing? There are traditional approaches, and these can be broadly categorized into two types. Static approaches, which mostly don't consider operation semantics. They generally use many-to-many graph isomorphism detection on call graphs and control flow graphs. And they use heuristics to match functions and basic blocks. And heuristics, there's an issue with heuristics, right? Like, they don't always give you the optimal answer. And otherwise, generally speaking, these graph isomorphism and graph matching and stuff like that, they're like hard problems. So you can't afford to do the optimal solution either, because there's like binary. I mean, the number of basic blocks in binary in programs can be like hundreds, even thousands, and even more. So yeah. So then they came up with dynamic approaches. This is like run it, see what happens, see what paths are taken, that kind of approach. So there's also dynamic slicing, which like when some events happen, you define like, okay, like this is where I will check or something like that. And tainting is basically like marking a piece of data, seeing how it flows through the program. The issue with dynamic approaches is that it does not provide complete code coverage, because like they have, of course, you have conditional logic and things like that, so you can't like go through all the control flow options. So yeah, the common issue with the traditional approaches is that they don't scale well, right? Like they're good, but just like the size of programs and everything is like now a challenge. So enter deep learning and machine learning, which is like anything you can do, I can do better. So they leverage graph representation learning techniques and incorporate code information into embeddings. Higher accuracy, because they can incorporate a lot more features than just like static analysis. It's much more scalable, and therefore they are, because they avoid like the heavy graph matching algorithms and stuff like that. Like they mentioned in the paper, they mentioned a few of the current like learning-based similarity detections. One of them is called inner eye. It basically works on a basic block level, and the issue with that is that it doesn't scale well. And there's another one called ASM2Vec, which works on a function level. So basically the issues, one last advantage that learning-based approaches have is like you can accelerate them using GPUs and other accelerators. So what are the problems with the machine learning solutions? There's no real work that does fine-grained. That's not true. Most work doesn't do fine-grained basic block level diffing. Only was inner eye, and even that it takes like 0.6 milliseconds apparently for comparing one pair of basic blocks. So like when you scale up to millions, it's like hours. And so yeah, they find that inner eye is not fast enough. Most of the others don't even bother with like doing basic block level. They just work on a functional level. So they also don't consider program-wide dependencies. So they don't look at like inter-function control flow. They just look at like within a function, they look at the control flow. So yeah, and most of the other works rely on supervised learning. One of the biggest issues with supervised learning for this type of workload is that it's really hard to come up with a good comprehensive data set but just because binaries can be so diverse, right? So like there's no like this is a correct data set kind of thing available out there. So yeah, one of the issues that inner eye has is, even though it works at a basic block level, there's they model entire instructions, like including operands, and like just one instruction is being modeled separately. This leads to an issue because like if you now run it with instructions that haven't been modeled, like it just won't detect them. And they have some numbers on the paper about like how inner eye doesn't do well when you give it code it hasn't seen before. So yeah, so this paper's approach. These are the issues, right? So this paper, for the first one, it creates embeddings based on basic block level. For the second one, it uses the interfunctional control flow graph to capture program-wide dependencies. And it uses unsupervised learning to create its embeddings. So you can train it with all sorts of stuff and it'll figure it out. So this is the basic overview of the, just a second, of the entire system. And it can be broken down into 3 major components: pre-processing, embedding generation, and code diffing. So pre-processing can actually be broken into 2 further parts, which is control flow graph generation and feature vector generation. So the interprocedural control flow graphs is what is generated in the CFG, and they use this data to like basically help them figure out which basic blocks are more likely to map to each other. And they also generate, in a pretty interesting way, they generate feature vectors for each basic block. And they do this by first modeling each instruction as a word. And they basically applied word to vec on each instruction. And they modeled operands, opcodes separately. So you can have variations on the same instruction modeled differently. And then after they model the word to, after they get the token embeddings for each operand and each opcode, they then combine it into a stream of instructions and they treat that as a sentence. And then they get a nice, they use NLP like algorithms to figure out what's what. So the first step, oh, my bad. So the first step is control flow graph generation. And to combine the call graph with the control flow, they basically combine call graphs with the control flow graph for each function, and it uses IDA Pro to extract the basic block information and generate this sort of ICFG. This gives a program-wide contextual information. All right, feature vector generation, the more fun and interesting part. What BinDiff does is basically it looks at, it creates a series of random walks through the ICFG it generated, and each random walk is limited to 5 basic blocks, and each basic block occurs in at least 2 random walks. So what they're doing is basically covering all possible control flow paths through their program. And then they serialize these, once they've generated all the random walks, they serialize it into one stream of instructions and they normalize it. And basically normalization is essentially just, they don't care about which register is doing what. So if it's a 4-byte register, like in x86E registers at 4 bytes, it's going to be called reg4. Our registers are 8 bytes, so they're reg8. And there's stuff, 1-byte registers, like R14, I think. No, yeah, R8B. And so you get the register with the size. Every pointer is just labeled as pointer, like PTR. They don't care about the value of the pointer. Any like immediate constants are labeled as IM, because they don't care about where exactly, what the value of the immediate is. An interesting thing to note is that string literals are retained. They don't get rid of them. and they say that it helps them locate like which basic blocks are likely to map to each other and stuff like that. So yeah, after normalization, they run word to vec on it, and word to vec as a softmax classifier. I'm not a ML person, so I don't really know much about this stuff, but they use continuous box of words. I forgot. CBOW? Bag of words. Yeah, bag, not box. Yeah, continuous bag of words version of word to vec. And basically that type of word to vec allows you to like have a target and then get information from around the target. So each instruction basically relies on its neighbors to give it more context. So every instruction gets its own sort of vector, right? Every instruction has its own embedding. Actually, each opcode and operand has its own embedding. Opcodes are actually, they use I forgot what the technique is exactly, but for each opcode, they weight it differently. Like for example, like the example they give in the paper is like, if you have a print function, if you do a O0 compilation, GCC uses 3 move instructions to set up the call for the print function. But if you use O3, it uses only 1 move instruction to set up the call. So they don't want to give move as much importance as a call. And so they have a classifier for assigning weights to different opcodes. And to generate embedding for one instruction, what they do is they concatenate the weight of the opcode and they average the operand's embeddings. So they concatenate opcode weight and average the embeddings of the operands, and then they average that again to get the embedding for a given basic block. You just sum up all the instructions for in the basic block, right? And then once they have an embedding for each basic block, they are now feature vectors that can be passed to the next type of machine learning algorithm that they use. So to get to the real embedding generation, they use text-associated deep walk. Deep walk is an algorithm which is an online graph embedding learning algorithm that considers a set of short truncated random walks as a corpus in a language modeling problem, and the graph vertices as its vocabulary. The embeddings are then learned using random walks on the vertices in the graph, and accordingly, the vertices that share similar neighbors will have similar embeddings. It excels at learning the contextual information from a graph, and nevertheless, it does not consider the node feature during analysis. So that's deep walk. Some guy came along, I think his name was Yang, came along and extended deep walk to text-associated deep walk, which basically also captures features of each node. So yeah, now we have 2 different ICFGs, and intuitively it just makes sense to just run text-associated deep walk on each one, but they found that it's not that great because it doesn't capture like common nodes that well. So what they do is they first merge these 2 ICFGs and create virtual nodes where there's a common node, and then they run text-associated deep walk on this. And the algorithm they use for that, and that can allow them to, now they can finally like start diffing the code. So they use k-hop greedy matching, and the reason they don't use linear assignment is because it does not consider the structure of the graph. And so with k-hop greedy matching, what they do is they initially start with the set of the common nodes, that the virtual nodes that they generated, And once they do that, they just basically go until you're done matching as much as you can with the k-hop. Whatever's left over is then linearly assigned, and they end up with 3 sets, which is one of set M over here is the match set, well, after the linear assign, and set I is the insertion, set D is the deletions, and set match is the total number of matched basic blocks. All right, evaluation. So the setup of their evaluation was Ubuntu 18, Intel Core i7, 16 gigs of RAM, and no GPU acceleration. The datasets they used were basically core utils, diff utils, and find utils. For core utils, they used 5 different versions, diff utils, they used 4 different versions, and find utils, they used 3 different versions. And for each one of these, they used 4 different levels of optimization, 00, 01, 02, 03. And they compared this to ASM to VEC, which is state-of-the-art learning-based bindiff. And bindiff is like the industry standard for static bindiffing. In RI, they compared it to this, but because it takes so long and it's slow, they ran it on limited tests because the size was really impeding the results they could get. All right, so they had to establish ground truth, so they used that's spelled incorrectly. They used Meyer's diffing algorithm, which is when you use diff, that's the algorithm they run, to perform text-based matching on the source code of where the object files came from. They only collect the lines that are identical, not the lines that are modified. And lastly, they just conservatively remove all statements that might lead to multiple basic blocks. And so this is definitely not a complete list of basic blocks or a list of differences that they'll get, but it's guaranteed to be sound. So yeah, and they also defined a bunch of metrics to evaluate the performance. M is the set of matching results from an algorithm, not necessarily deep bindiff. G is the ground truth of matching. MU is the set that represents the basic block matching pairs in which no basic block ever appears in the ground truth. This is possible because they eliminated some statements that might create multiple basic blocks. And MC is the intersection of M and G. So MU minus M minus MU minus MC is just incorrect matches because we know they're not supposed to be in the ground truth. So they measure precision by MU, so MU intersection M intersection G, which is which is MC, and they add the incorrect matches to basically what percent did I get right, and recall is how much did I actually get. So yeah, the first result they talk about is a cross-version analysis. As you can see, the bold numbers are the best recall and best precision, and almost everywhere except like one place maybe, deep bindiff is the best in terms of precision and recall. The next thing they look at is cross optimization. That's a lot of numbers, but generally speaking, all the bolds are under deep bindiff, which is good. They're trying to say they're the best and they're proving it with numbers. All right, I'll come back to this one. Efficiency. So one of the important aspects that they had was reducing runtime. And as you can see, like obviously size of the binary increases, it's going to scale, it's going to take longer. But for the largest binaries, it still takes about 1,000 seconds, which is like about 15 minutes, give or take. Definitely less time than I've talked for.
All right. Evaluation and comparing to state of the art. This is inner eye. They only did small sizes, but even here you can see that deep bin diff has better results than inner eye, and this is because they also take into consideration the control flow across functions. Yeah, and lastly, I want to come back to this parameter selection. They have two parameters, k for the k-hop graph matching, and the threshold selection for when they consider certain things to be a match. They tuned these things and they found that K4 was the best one, and threshold 0.6 was the best. Assumptions that they made, only strip binaries, no source or symbol information was passed in the binaries. Binaries are not packed, and so like if you want to run it, you unpack it first and then you can run it. And currently they only support x86, but they mentioned in the paper that if you just abstract it to the IR level, you can do cross-architecture comparisons. Limitations, optimizations that, so compiler optimizations can possibly like eliminate basic blocks for you and just make like a giant basic block. And deep bin diff doesn't fail, but it can't recognize those as well as if they did have separate basic blocks. Optimizations that change control flow drastically will also affect deep bin diff, and the second one will actually affect it more because deep bin diff relies more on control flow than the other matching algorithms, and there's no support for cross-architecture diffing. That's
Do the
just
other methods support cross-architecture?
they mentioned that some others do. So I'm not sure. I forgot the names of which ones do, but there are some that do. So yeah, thank you.
Okay, great, thanks. Questions, anyone? How many of you know about the concept of embedding?
Oh, I can mention that because I didn't know about it,
Okay,
and
so
I
you
had
read up on it?
to look it up.
Okay.
Embedding is basically coming up with a vector representation for your item, right? Like so, there's a crash course by Google, and they have a 15-minute video on embedding, and I think the first 5 minutes they talk about different movies, and in those different movies they mention like if you have a bunch of animated movies and a bunch of like blockbuster movies, and you have a bunch of adult movies, and you want to line them up, and you put them on a number line. Like on the left you have animated movies for kids, and on the right you have like adult movies, right? And so you can recommend, and you want to make a recommendation system. You basically line them up on this number line, whichever one is closest, you can basically recommend that. But now you have like other features like, okay, what if you want not just kids movies and adult movies, but also like if it was a successful movie or like it was an art house movie, right? And so you can add another dimension, and basically like I think the movie examples they used were Star Wars, Batman, some R-rated movie, Deadpool, I think. And so basically the blockbuster movies will be on its own axis when compared to art house, and then kids movies and adult movies will be on their own axis, and then basically where on this graph you lie is your embedding, and then you can scale it to like n dimensions if you want. Hopefully that kind of makes sense.
Yeah.
The Google person makes more sense.
Yeah, okay. So firstly, thanks for presenting this. This was one of the harder papers on the list. Okay, so the concept of embedding is I guess it started out with something that you mentioned in your talk called word-to-vec.
Oh, yeah.
And word-to-vec was this concept where imagine you have a language with lots of words and all, so commonly they are represented as many different ways you can represent words. Maybe you can assign them different IDs, like in the dictionary, or maybe you can represent them as a one hot vector and all. But around, I guess, a decade or so ago, concept emerged that what if we can take these words and map them in vectors in a real number Rn space. Okay, so you say, let's say I'm going to map words into a 100-dimensional real space. And the way you kind of do it is the following, that imagine that your input is the encoding of the word and let's say the one-hot vector, and I'm going to have a neural network which maps it into a real vector, and then I have another neural network which takes that real vector and maps it back to the word, okay, or actually more generally, not just a single word, but the word together with, let's say, a few of its neighbors on either side. And then I train this neural network. So the idea is that I'm going to learn a way of encoding my one-hot vector or one-hot vector for a segment from a sentence, so that I can map it to a real vector and then I can get it back. So then the encoder becomes what is called as word-to-vec. And in fact, there are, you can download standard word-to-vec encoders like this. Stanford had one, and now every major company, Facebook, Microsoft, they all have different kinds. The nice thing that they discovered is that when you map words to vectors, then they maintain the mapping has some semantic value to it. So like nearby words map together, or the distances between words represent some semantic distance, like the distance between queen and king might be the same as the distance between man and woman. And that concept, what started out as word-to-vec, has become very powerful because people have discovered that the same kind of thing can be applied in many other settings. So you'll often see things like X2vec, where X is generally arbitrary stuff. In case of what this paper is doing is, in the graphs, you can think of, after they have normalized the language, you can think of them as sentences in a language, and then they're taking from those random walks little segments which are kind of like sentences. Now, in natural language, what they do is to go from word-to-vec to sentence-to-vec. What they often do is they'll take the sequence and then just add things up. So the idea is that the vector corresponding to a sentence is basically just an addition of the vectors corresponding to words. There are many different ways you can concatenate. So this one is kind of using literally the word-to-vec.
I have.
Yeah. Yeah. Okay. So.
Yeah.
But I've seen similar kind of things in other contexts. Like for example, for detecting anomalies in a network. So what they do is they take the packet trace. We have a couple of papers like this, right? And you think of the if you have a packet to vec, then you can take a packet to trace, and then you can map that whole packet trace to a vector, and then you can see whether the traffic, whether for your particular traffic, the corresponding vector is closer to normal traffic or anomalous traffic. So they use it for anomaly detection. So a lot of security applications nowadays are also using it, as are other places. I mean, ML has sort of penetrated every place else. But kind of at a high level, the concept is I'm taking this discrete space and mapping it into a real number space, and in a manner which preserves some notion of some semantics which is useful for that context, meanings of the word, or whether something is good or bad, or things like that. So kind of a powerful technique. I don't know, does Professor Jonathan Paul's course cover this sector? All these things? No? Okay. Well, the NLP courses typically do cover, but it's a pretty powerful technique. So anyway, thanks. So last one.
Good afternoon. Today I like to introduce the a kind of figure printing method to make apply it to keyless system. Now let's see the introduction. The keyless entry system enables a driver to unlock the car without insert insert a key. And there are two traditional keyless system. One is called PKE. This system is passive because you don't need to push any button on your key. You just need to get near the car and open the door of the car and touch the door of the car, and it will automatically open. And another is called RKE. This system you need to press a button on your key. Now let's see the state of the art. That is what the mechanism behind the keyless system. There are two methods. The first is pre-shared long-term secret. That is the manufacturers of the keyless system will previously stored a long-term secret in the memory of the key, and the second is key rolling codes. That just like the verification codes that we used when we log in the web. It will keep changed to make it secure. Now let's see the limitation of the previous technique. Firstly, it's hard to defend the relay attack because the adversary can use the two counseling in concert to extend the original range of the RF communication between a vehicle and its key fob. Another thing is that the long-term secrets can be compromised. Thirdly is that the adversary can exploit a particularly vulnerability of the cryptographic algorithm. That's and used algorithm. Now let's see the analysis of the attack. The reason why the previous keyless system can be attacked is that firstly, the radio frequency signals emitted from the key fobs can be relayed or replayed. Another is that the extension of the communication range by relaying or forwarding a signal ultimately enabled the attacker to unlock the doors. The solution to prevent the attack is that firstly, exploit one of the radio frequency fingerprint technique. That's just like the Mac of our computers, or when we connect to the Wi-Fi, each device will be get a Mac, right? The RF fingerprint is just like the Mac. Yeah, because as we analyze, the attack is based on the relay of the RF signal, but the address and you can also called the RF fingerprint are different from the legitimate or malicious are different. So if we can detect the RF fingerprint, we can distinguish which is malicious and which is legitimate. Now let's see the background. That is in PKES system, vehicles periodically broadcast low frequency signals to check if there is a proper key fob is near the car. And in the RKE system, when you push the button and you will transmit a RF signal. Now let's see the principle of digital communication. The information source usually is binary code is encoded to be delivered, and then the encoded binary information is mapped into a symbol and conveyed to an analog RF signal. Thirdly, we use FSK, frequency shift key, and ASK, amplitude shift key, to modulate RF signals in keyless entry system. The difference of FSK and ASK is in FSK we manipulate the frequency. That means we can regard it as we add the information to the frequency, and ASK is we add the information to amplitude of the EM wave. Now let's see the new system model. Actually, the difference of the new technique between and the original ones is just add a holder. The holder we equip the holder with an RF receiver and integrate with BCM. BCM is the controller of the accessories of the car. Without the without holder, we cannot distinguish the RF fingerprinting. Now let's see the attack modules, because we need to verify if this system works, so we need to do some experiment and simulations. The first step of the simulation is build attack modules. Usually we build 3 kinds of modules. The first one is single bound relay attack. The third is a dual bound relay attack, and the third is cryptographic attacks. Now let's see how to implement holder. Roughly it includes 2 steps. The first step is training, and the second step is detection. We use a legitimate key to training it to get a classifier, and they use the classifier to distinguish the input RF signal. Usually, we see it depends on the value of the SV classifier. We can set a threshold. If the value is higher than this threshold, we regard this RF signal, the source of this RF signal is a legitimate key. Otherwise, it's malicious. Now let's see the evaluation step. The evaluation step mostly focus on detection. To test the hardware. To test the hardware, we firstly set up. This paper based on rail cars, and we also build a RF signal receiver and transmitter. It's two types of software-defined radio device. And the second step is a single band relay attack detection. That means we simulate the single band relay adversary, and to see if it can detect this attack. And the dual band relay attack, and the principle of the dual band relay attack and the playback attack detection is similar. The process is that to firstly we use the RF receiver to receive the signal from the simulate adversary, and then use a classifier to make a judgment to verify it, and to see if the hardware is tolerable to the environmental variations. We do more experiment. The first environmental variable is the temperature, and we put the hardware in different under different temperatures, and to see the value of FPR. FPR means false positive ratio, and the result shows that the FDR is nearly zero. So the temperature variation is not hugely affect the function of each hardware. Another variation is battery aging, because as we know, with the time goes by, the ability of the battery may change. So we use the different batteries and to test the function. The principle is similar to the previous one, and it also shows that the battery engine is it also shows that the hardware is not sensitive to the battery engine change. And the execution time is also we care about, because if the execution time is too long, it may bother the user. It may reduce the user experience. So we run it on different platforms, and usually the delay time is 4 microseconds, or from 5 microseconds to 50 microseconds. As we know, if the delay is less than 500 microseconds, the users usually cannot recognize. So it's also not a big problem. Now let's see the conclusion. Actually, the main job of this paper is introduce harder. Harder is extend RF fingerprint technique, and the paper apply it to car lock system. The paper do a lot of evaluations. Through the evaluations, it shows that the hardware is able to effectively detect and simulate attacks, and it is also tolerable to the environment change. That's the rough idea of the.
Okay, thanks. So, questions, anyone?
Please. Yeah.
So how is hardware still able to detect attacks if the classifier is only trained on legitimate signals?
Yeah, you mean how does it detect it?
And how does it detect attacks? Because like in one slide it says that the classifier is trained on only legitimate signals.
Yeah, it is trained by legitimate keys, and
Can you speak up, please?
Yeah. So how does it know what the out of class like? We are only showing it the samples of what is a good key, right? We
Yeah.
are not showing it samples of what are bad keys. So how is it learning to distinguish good from bad?
It depends on the classifier, the output of the use the.
So is it learning like?
It's based on hardware imperfection. So they have a fingerprint based on the header file of a signal, which is actually dependent on the microcontroller of a key form. So they that is one of the weaknesses
So what?
also.
No. I guess the question he's asking and what I'm also asking is following that if you're only training on the
Yes.
known key, so what were the examples in the training set of the unknown key? Like, I mean, how are they introducing?
So they have created a attack scenario using HDRs, and then they are trying to do all the possible attacks, and they have used a system without header and proved that all these attacks are like 100% accuracy of the attacks. Then they implemented header on that and ensured that what is the.
Oh, so using SDRs, they have implemented
Yeah.
other. They created attacks.
Yes.
Okay. So, yeah, I mean, generally this. So in this case, what features are they picking up? I mean,
They
the
are
fact.
using 3 spectral based features. One was SNR, peak frequency, and carry frequency offset between the receiver
And the transmitter.
yeah.
Okay. Yeah.
And then kurtosis and spectral whiteness as well.
Yeah. I guess I've seen in other contexts also features like the jitter in the carrier of the transmitter. So yeah, because apparently the
One paper earlier was mentioning similar.
yeah. So, but yeah, generally this idea of like using RF fingerprinting to isolate or to figure out or whatever de-identify transmitters is something which is so even our phones and all in principle, I mean, you could anonymize everything and all. I mean, probe and all the things you can. They all have unique signatures in terms of the low-level RF characteristics. Hard to pull off, but doable.
Yeah, maybe it will be better if they can train it by the adversary data set, not just legitimate
Well, I mean, you'll never have the adversary data set, so you always have to create your own.
Yeah.
I mean, it's usually, the attacks almost by definition are rare, so it's not that you are going to have training data sets with genuine attacks.
Maybe a little bit difficult.
Any other question? Okay, great. So, this is what will happen next Tuesday. We don't have any class, but instead you will have a non-programming, think of it like a take-home thing, just covering all the concepts in the course, open book, take-home. Okay, so no class. Thursday we have 5 remaining papers, so I'm going to have the papers out by tomorrow morning for sure, hopefully by tomorrow. And for the project presentations, so since for whatever reason this class was not assigned a final exam slot, so my original plan of having using a 3-hour slot for that is not going to work out. So I'm basically going to have a whole bunch of slots, and I know we are all kind of worried about the virus and stuff like that, and also if you guys just want to do it over Zoom, which is probably more convenient during the finals week, we'll probably just do that. So bunch of slots, and just each team can just sign up for a slot and do the presentation. So anyway, that's the plan. So I'm gonna, since not everyone is here, so I'm going to send out an email. And I guess the final bit of logistic is submission of the programming homework. So I'm going to send out the details. I'm still kind of working through something in grade scope, but worst come to worst, the submission would be through a Dropbox link. So wait. Okay, great. So see you guys next week.
Is the exam, is it like an exam or something? Like a take-home?
It's a take-home homework. I mean, it's basically, so there's not going to be any programming. So rest assured, just that you sat to the lectures and can solve simple analysis over that. Okay?